So impulse sampling is one way to create a sampled signal from a continuous time signal. Let's talk about another way to do it. Another way to do it is with what is called a zero-order hold filter. And a zero-order hold filter works kind of like this cartoon right here. Starting with some continuous time signal, if we run it through a zero-order hold filter, what comes out is this solid line over here. It kind of looks like this staircase signal. And it's called a zero-order hold because what this filter does is it grabs a value of the signal. In this picture over here, the signal was this dashed line, and it just holds it. And then it grabs it, and it holds it, and it grabs a value and holds it. So impulse sampling, we would get a value and it'd be an impulse at each one of these sampling times. A zero-order hold filter returns a signal that has kind of this staircase where each sampled value gets held until the next sample time. This still accomplishes our goal of getting down to a signal that we can describe by a list of numbers. This signal over here, we need to write down an infinite number of values because on any interval of time there's an infinite number of different values to write down. Over here on the right, we have accomplished our goal of sampling because this whole time interval here, which actually has an infinite number of values, all those values are the same. So I can write down one number for this, and I can write down one number for this, and one number for this, and one number for this, and one number for this, etc. So zero-order hold filtering accomplishes the same goal in that it gets us down to a signal that we have a finite list or a countably infinite list of numbers that we can write down. And it works just by sampling at a given time and holding it till the next sampling time. That's why it's called a hold type filter. So how can we model this mathematically if we want to think about how this actually works a little bit more rigorously? Mathematically, what we're doing up front is very similar to before. We're taking our continuous time signal x of t and we are mixing it or multiplying it by an infinite pulse train. So at this point right here, you can think of this actually as x sub delta, an impulse sampled signal. But this impulse sampled signal is now going through a low-pass filter. And a low-pass filter, one way to do a low-pass filter is with an impulse response that is a pulse function. So these impulses come through this low-pass filter, whose impulse response is a rectangular pulse, and what comes out is this staircase signal, because for every impulse that comes in, a rectangular pulse comes out. So mathematically, we can think about a zero-order hold filter as this whole block diagram right here. And we could go through the math and work through all this exactly like we did for impulse sampling to understand what this signal looks like in the frequency domain. We're not going to go through all the details right here. We're just going to sketch some pictures to get some intuition about it, though. And we'll do that here on the next chart. So here is what the amplitude spectrum of the zero-order hold filter looks like. Like I said, it is a low-pass filter, so it's going to pass low frequencies and reject high frequencies. And the blue line right here is actually a plot of the zero-order hold filter for some fixed sampling time. So you can see here 0 is DC. So DC or constant signals get passed with a gain of 1. And then as frequency goes up, the amount of attenuation on these higher frequencies goes down. So this is why this is a low-pass filter. And this region right here that I've kind of boxed in for the example we're going to look at is kind of the omega s over 2 region. So when you're doing digital stuff, the only thing that matters is between plus or minus the sampling frequency over 2. So we can see that any frequency components that we have are going to have this low-pass taper put on them due to the zero-order hold filter. So what happens when we sample a signal with a zero-order hold filter? Well, the same type of thing happens. Given some starting spectrum, when we sample it, this spectrum is going to get replicated up and down the frequency axis at multiples of omega s. The difference between impulse sampling and zero-order hold sampling is that these images, that's what we call these multiples of the sampling frequency, the spectrum at these multiples of omega s, they don't come through perfectly. Normally we would have a perfect triangle here, and a perfect triangle here, and a perfect triangle here, all up and down the frequency axis. Because of the low-pass nature of the zero-order hold filter, what happens is these frequency components get rejected. And in some ways that's a good thing. We don't want to have these images here, because if we ever want to reconstruct the signal, we have to go back and low-pass filter it anyway. So we don't mind that these get knocked down, because when we sample, we really don't care about those anyway. What is important, though, and it's a careful thing to think through and something we need to understand, is what happens to the spectrum here that should represent our original signal spectrum. So normally when we do impulse sampling, this triangle shape gets placed here and it looks just like the original shape. However, due to the low-pass nature of the zero-order hold filter, we get a little distortion. You can see this is a little bowed now. And it's bowed because of the previous slide where we noted that the zero-order hold filter is a low-pass filter, and it doesn't pass all frequencies with the same gain. It passes 0 DC with a gain of, or 0 frequency DC with a gain of 1, and as you go higher, up and up and up, it starts knocking down the frequencies more and more. So this distortion right here that the zero-order hold filter has introduced is not desirable. It's not something we like. We wish it hadn't done that, but zero-order hold filtering is kind of a more practical way to generate a sampled signal, since it's something we can actually do in the real world. We can't generate perfect impulses in the real world. But this is something you need to think about when you do zero-order hold sampling, that you actually are distorting the original signal spectrum a little bit. And how much you distort it is a function of how much low-pass filtering you're doing. It's a function of your sampling interval, capital T. So we now know two ways to create a sampled signal from a continuous time signal x of t. We can do impulse sampling, and impulse sampling is kind of the nice, pretty theoretical way to do it. Or we can do zero-order hold sampling, which is a little bit more practical of a way, but it does have some kind of non-idealities associated with it that you need to be aware of.